Now we will define the addition and scalar multiplication in component form. If we have two vectors, for example, A with components A1, A2, A3, and B with components B1, B2, B3, then the sum of these two vectors, A and B, is denoted simply by A plus B, and its components is given by this formula. So the first component of the sum is the sum of the components of the summoned vectors. And the second component of the sum is simply the sum of the second components. And the third component of the vector is simply also the sum of the third components. In a similar fashion, we can define the difference of two vectors. For example, A minus B is simply defined by this formula. And we can also define the scalar multiple of a vector A. For example, if C is a scalar, then CA is a scalar multiple of A, is defined by this formula. Let's see an example. In this example, we're given two vectors A and B. We want to find the length of A and some vectors, for example, A plus B, A minus B, 3A, and is some combination of A and B, for example, 2A plus 5B. So A plus B can be calculated by using this formula. So the sum has the components 2, 1, 8. Similarly, we can also calculate the difference and the scalar multiple of A and the combination 2A plus 5B. Let's V sub n denotes the space of all n-dimensional vectors. Means V sub n is a set of all vectors of this form, where each component is a real number. Proposition 1. If A is an n-dimensional vector, then for all scalar C, this equation is true. The left-hand side of this equation says the magnitude of the scalar multiple of A, and the right-hand side is the product of two quantities, one of which is the absolute value of this scalar, and the second denotes the magnitude of A. Let's see the proof. Let's consider a vector A with n components, A sub 1, A sub 2, all the way up to A sub n. And then by definition, the scalar multiple of A has components C A1, C A2, all the way up to C A sub n. And the length of this scalar multiple of A is given by this quantity. Now, if we do some algebra, if we distribute the squares over the quantities, then we can get this expression. And if we then factor c squared from each of these terms, we get this one. And then we apply the distributive law for the square root over multiplication, then we get this expression. It's simply, so the quantity here, the positive square root of c squared, can simply be written as the absolute value of c, and the rest is simply by definition the magnitude of A. This is the end of the proof of the proposition 1. Proposition 2. If A is an n-dimensional vector, then A is 0 vector if and only if the magnitude of A equals 0. Note here, the 0 here is the vector 0, which has all the components 0, and the 0 shown here is the number 0 or scalar 0. So the proposition says a 0 vector has magnitude 0, or conversely, any vector that has magnitude 0 must be a 0 vector. So it's an if and only if statement. Let's see the proof. Let's first prove the forward direction. Means if the vector is a 0 vector, then its magnitude must be 0, which is very obvious. Since all the components of the 0 vector is 0, if we square them and add them, then take the square root, we simply get 0. So the magnitude of the 0 vector must be 0. Conversely, suppose we have a vector A, whose components are a sub 1, a sub 2, and all the way up to a sub n, with the property that its magnitude is 0. We want to show that the vector A must be a 0 vector. Means all the components are 0. Since we have the magnitude of A is 0, so we can assume that the positive square root of the sum of the squares of the components must be equal to 0. Then if we square both sides, get rid of this square root symbol. And this is a non-negative quantity. It can only be 0 if all the terms we see here are separately 0. This completes the proof. Now we see some properties of vector addition and scalar multiplication. If A, B, and C are n-dimensional vectors, and C and D are some scalars, then these properties are true. The property 1 says A plus B equals B plus A. This is called the commutativity of vector addition. And the property 2 says A plus B plus C equals A plus B plus C. This is called the associative law for addition. And property 3 says that A plus 0 equals to 0. And 4 says A plus the negative A is a 0 vector. And the property 5 says that scalar multiple of the A plus B equals to the scalar multiple of A plus the same scalar multiple of B. And the property 6 says that if you have two scalars C and D with a sum, then the vector A distributes over the scalars C and D. So the difference between the properties 5 and 6 is here. In the property 5, we have a single scalar, two vectors. So the scalar distributes over the vectors. In the property 6, we have two scalars and a single vector. Here, the vector A distributes over the scalars. In the property 7, we see that if we have two scalars in an ordinary multiplication, it can simply be written in this form. So CD times A is simply C times dA. So we can regroup the scalars over a vector. And property 8 says that this spatial scalar multiplication, 1A is simply A. We'll prove some of them, and the rest will be given as homework for assignment. Let's take two vectors A and B with components as shown. Then by definition, A plus B is this vector with components as the sum of the components of the given vectors. Since a sub 1 and b sub 1 is a scalar, we can write the sum a1 plus b1 as b1 plus a1. Commutative law can be applied for real numbers. And we can do the same for the rest of the components. But by definition, the line here is the result of the b plus a. So we arrived at the conclusion that a plus b equals b plus a, which is called the commutative law for vector addition. In two-dimensional space, these two particular vectors with components 1, 0 and 0, 1. And in 3 dimensions, these vectors with components 1, 0, 0 and 0, 1, 0 and 0, 0, 1 play a very special role. So we denote the vectors as shown here. These vectors are called standard basis vectors. In two-dimensional case, this vector with component 1, 0 is pointing along the positive x-axis, and the vector here is pointing along the y-axis. Similarly, in 3 dimensions, the vector with components 1, 0, 0, which is denoted by the boldface I, is pointing in the direction of the positive x-axis. Similarly, this vector, the j vector, is pointing along the direction of the y-axis, and the vector with components 0, 0, 1 is pointing along the direction of the z-axis. These vectors are called standard basis vectors. They all have length 1, and as mentioned, they're pointing in the direction of the axes, as shown in the figures. So let's have a vector A with components a1, a2, a3. Then this vector can be written as a sum of these 3 vectors. The first vector has the first component a sub 1 and the other 2 components are 0. Similarly, the second vector has the second component a2, but the first and third components are 0. And the third vector has the third component a sub 3 and the first and second components are 0. By the property of the scalar multiplication, we can factor a sub 1 from the first vector out, and so in the cases of the other 2 vectors. Now we notice this vector a1, 0, 0 is the I, and the 0, 1, 0 is j. Similarly, the vector 0, 0, 1 is k. So we've written the vector A, whose components are a1, a2, a3 in terms of the standard basis vectors. Now we define a spatial vector called the unit vector. A vector whose length is 1 is called a unit vector. Just a moment back, we saw that the spatial vectors I, j, k, the standard basis vectors, have length 1. So they are unit vectors. In general, if a non-zero vector A, then the vector u defined by this formula, if you divide the vector A by its magnitude, you get a vector. This is a unit vector. So we can see the proof here. If we calculate the magnitude of the u and apply the property of the scalar multiple at the proposition 1 from the previous section, we get 1. So u has the length 1. And since the c here means the factor 1 over the magnitude of A is positive, so the vector u must have the direction as the same of the vector A. Let's see an example. We want to find the unit vector in the direction of the vector 2i minus j minus 2k. So let's denote the vector by A. And then we can calculate the magnitude of A, which is 3. And then the unit vector in the direction of A is given by the formula you see here, which is A over the magnitude of A, which simply gives this vector. The first component of which is 2/3, and the second component is -1/3, and the third component is -2/3.